emergency supplies into inaccessible areas.
Good morning, ladies and gentlemen. I'm Tyler. I'm Becca.
I'm Cooper.
And I'm Micah. And we are the Rescuers. Together, we have developed the Rescue Pod. Our idea to help disaster victims, such as those who are impacted by Japan's earthquake and tsunami. Even with the very best emergency response systems in the world, the U.S. Army National Guard takes 3 to 5 days to begin to distribute supplies. That is because they distribute huge amounts over a long period of time. Our airborne delivery method has a much faster response. We started with this hypothesis. If we design a pod and parachute-based delivery system that can land within 400 meters of its intended target, then we can deliver 48 hours of supplies to disaster victims who cannot be reached by land or water.
To learn what supplies are most urgent in disaster, we first visit the Red Cross. Priorities are food, water, sanitation, first aid, and shelter. Next, we went to the U.S. Army National Guard Armory, where Staff Sergeant Comer gave us guidelines from the U.S. Army Field Manual. We followed the guidelines from both these sources. We showed Sergeant Comer our original concept drawing of a shuttlecock-shaped delivery system. After a quick lesson on drift, we decided this design would catch the wind and sail off target. After considering many alternatives, we came up with a dense and compact design that could float, is watertight, and could be tightly packed. Next, we went to the post office and weighed our payload. Its weight would help calculate what type and size of parachute to use.
To learn more about delivering supplies by parachute, we went back to the armory. This time we talked to Sergeant Yoki, a Pathfinder and air job specialist. He explained that parachute size is based on payload density. Our pod is very dense at 0.2 grams per cubic centimeter. Sergeant Yoki taught us how to calculate drift, which is a factor of wind direction and speed, payload density, and altitude of drop. To minimize drift, we plan to drop the rescue pod from 2,000 feet. Next, we visited Mr. Urban Moore of Teaching Skydivers. Based on our payload, he recommended that we use a drogue parachute, which is about 5 feet across. We estimated that the drogue gives lower payload to a safe rate of descent of 25 feet per second or less.
To test our hypothesis, we lowered our supplies into the pod with thermal salt to the drogue. We did a pre-flight briefing and found that the winds were swirling at 2,000 feet. We decided to go ahead with the retest, but drop at 1,500 feet. When the flight crew tossed our pod out of the plane, we used cell phones and stopwatch to time the descent. I called out start when the pod came out and stop when it hit the ground. Each of my teammates reported their times and I recorded them. Then we calculated the average, which was 23.51 seconds, or 63.81 feet per second. Next, we inspected our payload in greatest condition on a predetermined scale. Although our pod had fallen nearly 3 times faster than expected, it was in excellent condition. Finally, we went to Google Earth to determine that our pod had only fallen 40 feet from its intended target. If rescue pods were scaled up and deployed in flocks, they would save lives, while larger organizations set up ongoing relief programs. We had successfully proven our hypothesis and had fun doing it.